is the idea that pops into your mind while we are uh, while we are talking about binary classification? Can anyone tell me what exactly binary? Uh, what do you mean by classification, or what do you understand by classification? Anyone? So, suppose we have a pot or something. Are people saying something? Okay. So, suppose we have a pot or something where we have different kinds of ball. Now we are trying to distinguish between those balls or the objects and put them into separate places where we can identify them distinguishingly that this is the kind A type of object and that another one is kind B type of object. Now, these groups could be happening in multiple numbers, right? There could be uh, three different colors of color of balls in that single pot, or there could be even more. But if there is only two classes or only two type of different objects which we need to classify or distinguish between, that scenario is something we refer as binary classification problem. So here we will have a data in each data from d dimension. So basically we have suppose xi to xn n number of data points for which we have to come to a conclusion, or we have to come to a decision where we'll be predicting or estimating if a particular object or the data point belongs to some class or not. So as we have only two classes, if uh, the particular object, suppose x1 is not belonging to a particular class, suppose class A, it will obviously belong to class B. So in this problem, in this section or the discussion, we'll be trying to find out how to. Could you please excuse me? So, yep. So we are trying to classify those objects into different classes. Now, what could come up with some situation where we can call it an error, or what do you get by the word loss in this binary classification problem? Anyone? What do you understand by binary a loss in binary classification?
Here loss means our predicted label is different from the true label.
Exactly.
We
So
automatically harm. Okay.
if suppose we have two buckets where we are supposed to put balls from the bigger bucket where we have a mixed data set, and I have put the black ball in a container which should have contained white balls. Okay, so this is the loss. And how can I estimate the loss, or how can I measure the total loss? Yeah, I'm sharing screen. Can you? Is my screen isn't is my screen visible?
Visible, sir.
Yes, sir.
Okay, so okay. Those who were not able to see my screen, I would suggest to rejoin. Okay, so uh, yes. So what should our goal be? Okay, no, what should the loss of the total once I have done with the classification, I have separated things. What should be the measure of? Okay, so what should be the measure of total loss? So, in simple way, I would like to take a mean of all those. misclassified objects. So the formula should be, and this is an indicator function. Here I have it has been shown that it takes it takes up two parameters. First is the predicted level, or what I have predicted about a data set, and what is the actual uh, outcome of that data of that particular sample point. Okay, so by yi I am actually trying to denote that what is the actual level. In supervised learning scenario, it is very evident that every data point comes with a label with it. So what is the predicted level of that particular data point, and is denoted by h of x, and y h of xi, and yi is denoted what is the given level of that particular data set. So if they are not equal, then this indicator function will uh, return 1, and if it is equal, then it will return 0. So can you tell me what is the sum of this indicator function actually denoting? This is a count. This is a count of something. Can you tell me what it is counting actually?
It's a count.
Number of misclassified points.
Exactly. So this is the number of misclassified point. So this loss function is actually measuring the fraction of misclassified points. So suppose I had 10 balls. I have misclassified 4 balls out of them. So 4 by 10 will, or 1 by 2 by 5 will be my loss, right? So this particular loss is called 0 1 loss or binary loss. Why? Because the the based on which function I'm calculating the loss is actually a binary function, which can produce only 0 or 1. Now, very obviously, uh, we should be always targeting for minimizing this binary loss. So our target should be in H linear, where for all H which belongs to H linear, we should be trying to minimize this 0 1 or binary loss function. Am I right?
Yes, sir.
Any doubt so far? Anyone?
No, sir.
No, sir.
Okay. So do you think it's a good idea to solve? Have you seen any similar kind of loss function minimization earlier? You must have, but can you name a few? In classification price, in linear regression, what we are trying to, we are also trying to optimize the MSE function, right? Mean square loss. There we were trying to optimize a squared loss. Now here we are going aiming towards a linear loss function. So can you find some similarity? Is it seems familiar?
Yeah, sir.
Okay. So it should also be feasible for us to solve the uh, problem in the same way, right?
Yeah.
But unfortunately not, because if you can recall, uh, in linear regression problem, we had a loss function which was taking real numbers into its parameters, right? Into its consideration. But here it is only taking 0 or 1 or binary levels, which makes it discrete, uh, of which makes its nature discrete rather than being continuous, just like linear regression problem. So basically the discrete nature of the loss function makes it not differentiable. So technically it is a NP hard problem in general. So how do you solve it? What actually we did in the case of linear regression problem? So we were trying to solve, um, we were trying to come up with such a line which will deviate, of course it will deviate the points. And what was it trying to do actually? It was also trying to like measure the distance, right, in different directions. Then that could also be used over here. We can measure the distance in both the direction, and we can label positive direction, we can label both the direction as positive and negative direction, and try to minimize the distance from the line. Or we can try optimizing the loss function. But if you can recall that the linear regression loss was also sensitive to the data points, distance of the data points from the line we are actually trying to come up with respect to the separator, right? So to deal with that, what will come up? So first, um, let me ask you a question. Suppose you want to know what is the time, what is the current time right now, and you don't have a clock. Okay, so suppose a ball wants to know in which pot it should be going, but it doesn't know anything. So let's come back to the time problem. You want to know the time and you don't have a watch. So what did you do? You're gonna ask your neighbors, right? Isn't it?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yeah. So similarly, if a point, if, suppose I have come up with a point which is x test, which doesn't come with a label. This is a point which is unforeseen to our earlier data set, and our first instinct should be, in simplest classification, that find the closest point to that particular extent point, test point, which should be x of x star. Okay, so suppose we have come up with a new point which is x test. So our first instinct should be finding a point in our existing data set which is x star, and tell that that particular testing points label should be equal to its nearest training points level. Okay, this is very vague and this is very simplest algorithm, but there are problems. So what are the problems? First problem is, if you are coming up with an outlier, suppose this is, wait a minute, yeah, this is the separator, and here I should be having all the plus numbers, and here I should be having all the minus. uh, okay, but here is a negative point over here, which is a outlier from this actual negative data set. And if I come up with something like this, mm, okay, if I come up like something like this, which is a testing point, and it will look for its neighborhood and it will find this particular number, a point which is a uh, negatively labeled. So what it will try, it will just not try, it will just tell that I'm a negative point, or my label should be negative, which is not that true often. To mitigate this problem, we come up with a KNN method, where not only based on one neighbor, will be uh, relying on more neighbors than one. Okay, so what I'll be doing here I'll be predicting y test based on few few other points level and take the majority among them. Okay, so suppose here we had few plus points as well, so I'll be taking all of them in count and do a voting who will so basically the number of majority, here in this case the plus points are in majority, so this unknown labeled point will show its identity as the majority only. Okay, cool, sounds cool. What was the problem in k while I was taking k equals to 1? So if I was relying on only one neighbor, then also it is a knn algorithm, but here k is only 1, and by increasing the number of k, number of the value of k, I am actually trying to mitigate the problem of susceptibility with outliers. But we also can't go and make k equals to n. Then it will just take all the points into consideration and always be giving the label of the majority points. Okay, so we need to come up with some particular k star. Okay, wait a minute. Some particular k star which is a good choice of k. Okay, so for such a choice of k which will not smooth out the majority, also not be that much susceptible with outliers. Okay, so choosing a k should be treated as a hyperparameter. Okay, smaller the k, complicated the decision boundary. Yes, so we are trying to come up with such a boundary beyond which our point will be labeled as something else, and on the other side we'll be labeling it with something else. And if we come up with smaller k, these things will be more susceptible with outliers and we'll be getting a complicated decision boundary. And larger k will give me will try to smooth out the effect of uh, actual neighborhood. So we need to come up with cross validation. So I need to check every time and come up with a k which is most effective. But what should be what I would be expecting as issues while dealing with KNN? So whenever we are going for a distance function, it is a very hard thing to find a distance function where we should come up with a particular thing, a particular function that will evidently tell me that this is the particular distance beyond which you shouldn't be consider a neighborhood effectable anymore. So this is very hard to find it over here. Okay, and prediction is computationally expensive. Why? Each time you are coming up with a new uh, test point, it is always taking all the existing data points we have in the data set to predict the neighborhood. So there is no basically underlying model. Each time we are going through the same process. Okay, so basically suppose I have come up with a new data point, it will again check the neighborhood, and after 1,000 years if I come with another data point, then also it will check the neighborhood only. It hasn't learned anything. This is basically repeating a process again and again. So each time I'm coming up with a new point, it will need all the previous test points to predict what is the actual level of the test data points. So that is not something we are trying to come up with, right? It is not actually learning anything. Rather, it is just going for an iterative manner. So to mitigate that, we'll come up with something else called decision tree. So here, based on few questions or evidence, we'll come up with a plot or a area based decision where we will be able to classify based on the location of the new testing points, irrespective of the presence of previous lines, previous data points. Suppose we have a data set xi yi, where yi is our binary labels and xi is our vectors, real real vector. Now in decision tree, if we put a x test based on few questions, obviously binary questions, yes no questions, we'll try to come up with some decision. Is there anyone? Okay. So, yeah. Now, based on that, we'll be trying to come up with a prediction or verdict. Based on the question, we'll be trying to come up with a verdict where we'll be saying that if that particular question is being answered by the test point as yes, it will surely be on positive or negative side of the uh, separation. Okay. So basically, a question is taking a feature and a value. Suppose I'm asking, I was asked to make two classes where first class will contain only the students having height more than 180 centimeter, and the other one will contain the rest. So what will be my key, like what will be my separation question, separating question? Is your height greater than or equal to 180 centimeter? If this thing is giving me a positive answer, a student will be classified in positive group, and vice and otherwise, right? Now, how do you consider a question is good? So there could be different questions or multiple questions which can come to same conclusion. Okay, and but how do we come to the conclusion that this particular question is better to ask a student rather than asking this? Uh, Anyone? Any direction?
Entropy loss.
Uh, could you please explain?
In entropy loss, we are calculating the goodness of the question, which feature and which data point should we choose. It should be give a less.
Exactly. So
Yes. Okay.
I got it. So basically, uh, each questions come up with a certain level of impurity in it, right? So of course, each question is taking you towards the decision, but few questions have more impurity than others. So there's always a possibility that a particular question will lead to misclassification. So we'll be choosing that particular question which has the least amount of risk of misclassifying our testing points. Okay. So we'll be trying to find that particular question which has the least impurity in it. Okay. So what he was actually telling, the entropy loss, basically uh, the name actually, the name of entropy came actually from statistical physics, lately used in uh, information theory. But what is the main agenda of this entropy loss? If some particular question is able to classify, okay, is able to classify all the points to zero or all the point to negative or vice versa is something is full of impurity, right? It's full of impurity. It is blindly classifying all the points to a particular class. But we'll be trying to find such convex function or such a function which will come to uh, equilibrium point, which will help to get us such a condition where there's no chance of impurity for any kind of data points. For that, we can use entropy loss. Maybe we can use Gini index as well. That is also something widely used. Okay. Now, this entropy could be measured in different ways. First, if I am being asked a question and based on that particular question, I am being classified in two different groups where I might be encountering more questions or um, that's the final decision. In both the scenarios, I could have made some mistakes due to the questions or due to the classification. So in both the sections, we have some entropy. But to measure which question is better than other, we need to come up with some such a mm, such a quantity which will which will be a combination of all this entropy and try to minimize them simultaneously, right? For that, we have come up with information gain, something from information theory only. So here what we are trying to do actually, we are trying to find entropy of D, the decision question, minus the gamma of entropy of S or entropy of positiveness plus 1 minus gamma of entropy of negativeness. Okay, where gamma is a hyperparameter which is the absolute fraction of gamma the uh, positive outcomes, positive levels, right? Clear so far? Now, this particular algorithm discretizes the feature in a mix mean and max range. So basically, the assumption is being taken that in decision tree, each feature will uh, oscillate between its mean value and max value. That is very evident. And we'll be picking that particular question first, which has the largest information gain. So, to converge to our actual decision as quickly as possible, we'll be trying to pick up the largest information gain attached question first, and then we'll go down accordingly and repeat the process for D yes and D no, which is positive class and negative class again and again with different questions. The the question having its information gain immediately less from the superior one or the parent question. Cool. You can visualize it like I have asked a question over here based on yes or no. I have asked another question which is also classifying them in into two groups. Okay. Okay. Now, how far should we go like this? Uh, that could be decided by how pure the question or the class is becoming after you ask a question. So, after reaching a certain level of purity, sufficiently pure state, After reaching a sufficiently pure state, we can stop asking questions. Even if there are few impurities in that particular state or in that particular nodes of the tree, we can stop asking question for the sake of simplicity, and we can say, yeah, it's cool, we can bear with this much impurity. Or we can decide what should be the depth of the tree by a hyperparameter. So we can tell that at max you can go up to 5 level or 6 level. That is, you can ask at most 5 or 6 questions to a particular uh, branch. Also, you can, I mentioned already, you can also measure the goodness of question by Gini index. Now, how it will appear at the end? So basically, suppose this is an example of decision boundary where, suppose I have asked a question if f1 is smaller than 5 or not. If yes, then I'll ask few more questions. If f2 is greater than smaller than 7 or not. If yes, then I'll ask few more questions like if f1 is smaller than 3 or not. If yes, then I'll tell that yeah, this is a class I'll be labeling it as 1, and all the other class accordingly. Okay. Now, so far we have seen no probabilistic assumption has been taken into account. But suppose if we have provided such a test data which is totally irrelevant from the train data, will this decision boundary will this decision boundary be able to do any good? What do you think? Suppose you have given a totally unforeseen data to be predicted by this particular set of decision boundary. Will it be able to come up with something good prediction? What do you think? Anyone? Okay, so of course not, because the model will not work because it is the data is exactly not matching and the texture of the data is totally a mismatch thing. So it will not do good. But if the test data is exactly same as train data, so it will come up with something memorization problem, right? And that will be of no good because for that particular thing we already have the data set. So practicality will be achieved if we can come up with some way to where we can connect the training data set with the past train data set. Sorry, test data set with the past training data set. And we need to impose some uh, assumptions over the modeling for that. And in that scenario, we can actually come up with two different model. One is generative model and another one is discriminative model. So what generative model does is, generative model comes up with the origination of the data points and it takes assumption towards the distribution or the parent distribution from which the data points are being retrieved from, whereas discriminative model only tries to model the data set which we have already based on the present uh, set of instructions and come up with a a decision. Cool. Any doubt so far? Sorry. Okay. So
Yes, sir. Can you just scroll a bit up
Yeah,
to
sure.
this?
Yeah.
Yeah, yeah. The
More?
classification, like the descriptive and generative models, right?
Yes, that part, right? Yeah.
Yeah.
So,
Okay.
uh, do you have any questions regarding this?
No. So for generative model, so we are dependent on the features, and for discriminative, we are dependent on the labels given the features, right? So just
No, basically, in generative model, what we are trying to do, we are trying to make some assumptions about the parent distribution from which the data being generated at the very first place. And based on that, we are trying to
mhm.
predict what will be the levels. But in discriminative models, we are not actually worried about the parent distribution and where the data is coming from. With the available
Okay,
instructions or the data set, we are trying to predict, and we are just trying to come up with some logic which will make us predict that if some new data points comes into the picture, what will be its level. Okay,
got it.
am I
Yeah,
making sense?
makes sense. Yes,
Okay.
thanks for that.
Yep. Oh, okay. uh, any questions regarding this? Yeah, go ahead.
Sir, could you please explain generative and discriminative model again?
Yeah, sure. So basically, in generative model, what we are trying to do, uh, okay. So suppose you have a data set. What do you actually know about that particular testing data set? Hello, are you? Am I audible? Yeah.
Yes, sir.
So suppose you have a data set. What do you exactly know about that particular data set, apart from given features? Initially, nothing, right? So you have given a data set. You know what are present in that particular data set, but uh, there must be an underlying distribution from which that particular data set has been derived, or someone has sampled, right? So in generative story, what we are actually trying to do, we are trying to uh, take assumption and uh, trying to work towards that particular parent distribution from which the actual data set is coming. And based on that uh, prior information, once we are able to fetch that information or assume that information, uh, based on that information, I'm trying to predict the levels of unforeseen data points, assuming that unforeseen data points are also coming from that particular parent distribution. So in this particular method or modeling technique, we have few prior information about the parent distribution. Whereas in discriminative model, we are trying to go towards the labeling or the prediction based on only the data we have in front of us. Okay, I guess you'll be able to understand
Yes, sir.
a little better if I can explain the next part. So let's proceed with that.
Yes, sir.
Okay. Hold a minute. Let me reshare my screen. Is my screen visible?
Yes, sir.
Okay.
Which week we are doing, sir?
Sorry.
Which week we are discussing?
Week 8 actually.
Okay, sir.
So now we can see here in generative story, what we are actually trying to do, we are deciding labels. So basically we are already predicting the uh, labels, and then we are trying to get into the features. So why this? Because based on that prediction, we will be able to model the features. Okay. So we are trying to come up with such a conclusion that if a particular if a set of features is coming up with a particular level, then it must be coming up from a particular distributional assumption. Suppose what I am actually doing over here, I am predicting the level first from a binomial model, or you can say it's a Bernoulli model, where it only gives me output in success or failure, or 0 and 1. Okay. Your spam classification example was given. If y is equal to 1, or the predicted model is 1, or the attached model is 1, it's a spam, otherwise it's a non-spam email. Okay. Now suppose I'll be checking for uh, presence of 3 particular words in the email, and I can create such combinations where uh, it's like a uniform distribution. It's coming from a uniform distribution where each the uh, sites, or each the combination comes up with a particular probability of appearing. Suppose it's a biased dice and I'm rolling it, and each time it's coming up with such a probability. Okay. And this particular die will be different for both y equal to 1 genre, or spam world, or non-spam world. So can you estimate the number of total parameters over here? What actually we are trying to like come up with? So in this model, we are trying to first predict the label, and then based on the label, we are trying to check the number of occurrence, or the probability of occurrence of a particular combination of a words, right, in a sentence or in the total email. So what will be the parameter in this particular model? First parameter is being used for the binomial one, Bernoulli one, that is the probability of success. And then as we are using a uniform distribution, it will always come up with 2d 2 to the power d minus 1, where d is the number of combination distinct unique elements, right? So d is the number of words in this scenario. So in this scenario, what will be the case? The total number of parameter will be 2 to the power d plus 1 minus 1. So this is something is taking us towards the generative story, and we are trying to generate the parent distribution from here. But in this particular scenario, the main problem is we can't estimate the parameters. We can come up with the parent distribution, but we can't, because 2 to the power d plus 1 minus 1 is a huge number. It increases exponentially with respect to d. So suppose if d is 10,000, it will be large enough that our computational power will extinct, right? So for the simplification, we are coming up with the assumption, that is class conditional independence assumption, which tells us that these words, occurrence of these words are not dependent to each other. It's always independent of each other, and they don't uh, affect occurrence of others. So this is basically discretizing all the parameters and ignoring all conditional probabilities. Okay, but what is the gain of that? First tell me, what is the thing I'm losing by assuming it? Can anyone tell me? What is the thing I'm losing in practicality? In real world, there's no such scenario where suppose in the sentence, in a spam sentence, if someone is mentioning lottery, there's a high chance that that same email will mention price or cash in that same email only. Okay. So they are not at all independent in real life, but we are assuming it for the sake of simplicity. And based on the rule of independence, we are able to estimate these parameters, and we are come up with a structure which is closed in closed form, and able to estimate these parameters with help of maximum likelihood estimator or MLE, which we have seen earlier, right? So in this section, what we have assumed in name of class conditional independence assumption is a naive assumption which will give us direction laterly. Okay. So now I'll ask Shukarna to please solve few PYQs from these topics. Shukarna, are you there?
Yeah, right. Thank you.
Okay. Yeah. So I would request to solve few PYQs so that we all can get to that point actually, and
Okay.
then I'll try to continue again.
Yeah, maybe, but then I have got the question paper as such. I have not divided it based on topics. We'll see if there is something that you are not sure, we can discuss maybe, or you can input or do something like that. Okay. This is actually Jan 2025 MLT question paper. We'll try to solve this question. That's what I thought. But then, uh, and I would like to actually like get answers from all of you. I'll give you a explanation. Not that I will not, but then uh, let us not just. I don't want to simply keep on speaking. Okay, so maybe if you could give me an answer, it will be easier. If we don't know, we'll go deeper into the topic, else we can, I guess, smoothen it out. Okay, this is the first. I hope you are okay with it. So what is the role of regularization term in the ridge regression? You can look at the options and tell me, but give me an answer with some explanation. Okay, I don't want, if you don't know the explanation, it's fine, but still, if possible, give me an explanation. Okay. So this is the first question of your question paper. Hello, someone, please. It's okay if it's wrong. I don't think anybody is really an expert here. Yes, please.
Anyone? You all
Okay.
have already gone through this rich regression and everything in quiz 2, I guess.
Yeah, it'll be too boring if I keep on speaking like a radio. Come on.
Yeah, ma'am. I think the second option is correct.
It penalizes large coefficients to reduce overfitting. Yeah, you're
Be-
actually right. Uh, do you know why? Have any idea why?
Because if we are using normal linear regression, some
Mm-hmm.
models give us overfitting. Because of overfitting,
Hmm.
my weights are increasing. My weights are more than increasing.
Huh.
That's why we are using this lambda or
Yeah.
regularization term to reduce it.
Yeah, perfect. Very good. Yes, usually if the model is actually able to learn unnecessarily a lot, okay, if it is even learning the noise from your data, then that would mean that your data is being overfitted. And to actually overcome this difficulty, right? To overcome this difficulty, we are adding a regularization term to our ridge regression so that it would penalize the large coefficients and reduce our overfitting. Okay, very good.
Ma'am,
The second question, yes.
ma'am, what is the meaning of penalize?
What is the meaning of penalize? Penalize means it is giving you a negative score, or you are being punished for making up a large coefficient. That is, you want to reduce that complexity where you are learning the unnecessary things, right? So you want to reduce that noise from your learning. So we are negating that effect. We are trying to add some noise, add some term, lambda term, into our model so that unnecessary terms are not learned.
Okay, ma'am.
Okay, great. Yeah, this is the second question. Which of the following conditions must be satisfied for a decision tree to be pure? Okay, so pure at a given node. Fine. So when is a decision tree said to be pure? That would actually give you one answer. When is a decision tree said to be pure? Yes, please. It's extremely okay if you're wrong. Please give some answer. When is a decision? He did the Sami brother just discussed, right? When did do you calculate the impurity, or how do you calculate the impurity?
Ma'am, third option.
Okay, all
Ma'am,
samples
third
at a
option.
node being to the same class. Yes, very good. Yes, if all of the nodes are being to the same class, then the node at that point is said to be pure in nature. Okay. So what can we? And there is one more option that is right. Yes, that's right. That's the definition of a pure node. And and what would be the entropy of a pure node?
It can be 0 or 1.
Zero.
Yeah, entropy of a pure node will be zero, right? There is no misclassification happening. And when will it be actually maximum?
When there is an impurity
Yeah, when the impurity is,
higher.
yeah, when the impurity is maximum, or there is an exactly mixed classification, equal misclassification of both the classes, right? 50-50 percentage of both the classes. That is when we'll have a maximum entropy. Okay, that, and the maximum entropy value that could happen is 1. Okay, and if you really want me to stop me somewhere, do that. Okay, your answers are right, that's why I'm not going too deep into it. Okay, now this is some question that you could answer with the first one, something related to the first one. Consider that there are 3 weight vectors that are learned for a 4-dimensional data set using a linear regression model or regularized linear regression model. You are given 3 weight vectors. You want to try and say which vector is a direct linear regression, which is a ridge regression, and which is a lasso regression. Looking at these weight vectors, decide which vector belong to which kind of regression. That is, whether it is linear regression, whether it is ridge, or whether it is lasso. What is the peculiarity of lasso? I guess that would be the easier part. What is the peculiarity of lasso?
Some data points can be 0.
Some weight can be zero,
Some
right?
weight.
It can,
Yeah,
yeah,
weight.
it can directly put, it can force a weight vector to actually be zero. So from this, which would be the lasso one? Actually, that would be
Third,
easier.
W3.
Yeah, W3. Perfect. Very good. This is going to be the lasso one. Then, now what about W1 and W2? What did we say just now? That why are we applying usually ridge? When is a ridge regression applied?
To reduce the weights, W1 is for
Ah,
regression.
yes. Perfect. Very good. Yeah. To reduce the weights, right? That is when you apply the ridge regression, when you really want to reduce the bias, that is when you apply the ridge regression. So W1 is going to be your ridge, what is it? Yeah, ridge weight vector, and W2 is going to be your linear weight vector because that has got a higher weight value. And since lasso can force some value to be zero, some weight values, some vector values to be zero, hence W3 is going to be a lasso vector. Okay. Uh, Please tell me if you want me to elaborate more or got some doubt. Okay. Okay, this is kind of a problem. So you are given a data set and you are given what are the three centroids, okay, using a Lloyd's algorithm, three centroids after the first iteration. Okay, you want to know into which of these clusters would the data point 3, 3 be classified after one more iteration. Okay, so the first step is to tell me what would be the centroids after the second iteration, right? In general, a Lloyd's algorithm would actually place the point or direct the data point into that centroid which has the minimum distance, right? That's how the Lloyd's algorithm works. So first that, in the next iteration, what do you want to know? You want to know which would be the proper centroid. So according to this data, this C1, C2, C3 given, what do you think, or which do you think will be the next center points? Can you give me the next center points? Only then can we calculate the middle value, I guess. So what would be the centroids in the next iteration? I probably will have to calculate, but at least tell me how to do. I can give you the answers. How to calculate the next centroid? How to calculate the next center point?
By calculating the mean,
Yeah, exactly. You're calculating the average values corresponding to each vectors, right? Each data points. So what you can do is to get the centroid of, yes.
Sorry to interrupt. Can anyone tell that which actual problem is being solved by Lloyd's algorithm? So basically, there's a problem which can't be solved in, uh, which is a NP-hard problem, right? And as an alternative, we are coming up with Lloyd's algorithm. But which actual problem is being solved? Anyone? It's k-means clustering, right? So we're trying to solve k-means clustering problem with help of Lloyd's algorithm. That's why we are trying to go forward with means. Shukana, you can continue.
Yeah,
Sorry
yeah,
to
got
interrupt.
it. Yeah, no, no, good. Yeah, thank you for the input. Okay, so as okay, I didn't notice a name, sorry. As the one previously pointed out, we calculate the mean to get the next centroid. So the mean values are calculated. So C1 would be 1 plus 3 divided by 2. That's going to be 2, right? 4 by 2, 2. And 2 plus 3 divided by 2, 5 by 2 will be 2.5. Okay, that's the first center point. For the next iteration, the center point for corresponding to C1 is going to be 2, 2.5. For C2, it will be 3 plus 5 by 2, which is 8 by 2. That will be
4
4.
and 4.
Yeah, 4, 4. Very good. And the next one is going to be 16 by 2, 8 and 18 by 2, 9. Right?
Yes, ma'am.
Yeah, so you have 3 points now corresponding to C1, C2, and C3, which are 2, 2.5, 4, 4, and 8, 9. What you want to do is you want to calculate the distance from these center points towards your data point. What is the data point that we need? Our data point is 3, 3, right? So you will calculate the general Euclidean distance corresponding to each of these centroids. Okay, corresponding to each of these centroids, you will calculate the Euclidean distance. That is 3 minus 2 the whole square plus 3 minus 2.5 the whole square. You will get an answer. Similarly, you can calculate for all three centroids, and whichever gives you the minimum distance, that will be where the 0.33 will be labeled. Okay, here the distance, the minimum distance is actually for the first centroid C1, so 33 will be assigned to C1. Okay, cool.
Yes, ma'am.
Okay, great, thank you. Here, a data set of 1,000 second-hand cars has four features. Okay, some x1, x2, x3, and x4, and the selling price seems to have this relationship, that is x4 square is equal to x1, x2 plus x1, x2, x3. If we want to project the data set into a lower dimensional space, which of the following task would be appropriate? Okay, so this is somewhere from the first weeks where you apply the principal component analysis, which is dimensionality rejection technique. Okay, any guess what is the answer? Or at least, do you use a standard PCA or a kernel PCA? Oh, come on. Do you use a standard PCA or a kernel PCA?
Kernel PCA.
Yeah, perfect. Why do you use a kernel PCA instead of standard one? Or what is the problem with the standard one here?
Yeah, actually, standard PCA works with the like linear structure of the data.
Ah, very good. Yes, the like the sorry, the standard PCA actually works with linear data. You already have a non-linear relationship as given in the model here, that is x4 square is equal to x1 x2 plus x1 x2 x3. Hence we do not prefer a standard PCA. Okay, and what are the degrees of every terms that you have here, every terms in this model? What are the degrees of the terms used in the model?
2.
Yeah, one is 2. Is that the highest degree?
and 3.
Yeah, this term actually contribute with 3 degree, right? X1, x2, x3. So what would be the minimum degree of your kernel PCA? What minimum degree of kernel PCA would you need to represent your data properly?
3 degree.
3 degree.
3.
Yeah, perfect. That's it. Since you have the highest degree as 3 in your model, to represent this into a linear dimension, okay, to represent it into a lower dimension, you at least need a kernel PCA with 3 degrees of freedom. Okay, I hope these questions at least seem simple. Okay, this is something pertaining to your last weeks. Weak learners used in the ensemble method typically perform slightly better than random guessing. Is it true or false? No, this is an easy guess.
True.
True. How?
It is the definition.
Yeah. Okay. The weak learners, what they actually do is they try to learn from their past mistakes, right? They try to they combine features like a boost or something. They combine the features. They try to learn from the past mistakes and perform better than the random guessing one. That is why they'll actually have a higher accuracy. Okay. Okay. Here, you have a set of data points generated from this model. There are two models fit into this particular data. This is actually the process is following a cubic polynomial, if you actually observe, and two models are fitted. One is a linear model that says y cap is equal to a0 plus a1x, and model 2 is a 5-degree polynomial that says y cap is equal to a0 plus a1x plus a2x square plus a3x cube plus a4 x raised to 4 plus a5 x raised to 5. Okay. Now we need to actually traverse through each of these options and say which of them are the correct options. First one says that, okay, even before the first one, we can actually decide these two. These are easier, I guess. Will model 1 underfit or overfit? It's a cubic process, and model 1 is actually a linear model. So would it underfit or overfit our data? What is it likely to do?
Underfit.
Yeah, it is likely to underfit, right? So this option is right. When model 1 is underfitting, would it have a higher bias, or will, okay, you don't even have to connect with that. Okay, will model 1 or model 2, which would have a higher bias, do you think?
Model 1.
Why? Yes, answer is right, very good. But
Uh,
why?
Model 1 is a underfitting model, and it just create a simple linear that linear line.
Yeah,
So
it is.
it has a high errors.
Yeah, it has got higher errors. It is not able to capture whatever is given in your third degree polynomial, right? The process completely. So it will have a higher bias. Okay. And which among model 1 and 2 will have a higher variance?
Model 2.
Why? Yes, correct. You're right. But why?
Model 2 is a overfitting model, and
Hmm.
it is just going through all the data points and creating a model complex.
Yes, it is creating a complex model, and hence what would happen is, if at least there is a slight change in your data set, right? The output will drastically change, and hence it has got a higher variance captured with itself. Okay, very good.
Ma'am, could you please explain this question again?
Yeah, sure. Okay, see, you have a third degree polynomial with you, right? That is your process. Your actual population is being fitted with a third degree work. Okay, third degree polynomial. That's how the process is working. Now, in the model 1, you just have a linear relationship stated between your output and the independent variables. That's how model 1 is designed, and model 2 will have a 5 degree polynomial defined with it. Okay, now what will happen is, you have a third degree process happening, and since model 1 is not able to capture that third degree level of complexity happening in the process, it is likely to underfit. That is, it is likely to learn less from your data. Okay, on the other hand, model 2 is unnecessarily complicating it. It is only a third degree process, and you are fitting it into a 5 degree polynomial. That is, you are trying to learn more unnecessary factors, which will imply that your model is being overfitted with respect to model 2. Is that point okay?
Yes, ma'am.
Okay, now about bias and variance. Since the model 1 is not able to capture everything that is given by the process, okay, there is more likely that your prediction would deviate from the actual value a lot more. Okay, there is a more chance that, that is what is called the bias, right? Your estimate is actually going very farther away from your actual variable. That will happen when your model is actually underfit. It is not able to capture that everything is happening in your data. That is why model 1 will have a higher bias. And about variance, what will happen is, since there is more complexity in your second model, even if we add a single data point into our data set, there will be more unwanted complications in the output, or complex calculations happening, due to which there is a high chance that there is a high variations in the predictions. Whereas, since the first one model 1 is an underfit model, it is only a linear model, and it is not bringing unnecessary complexities. There, even if we add some more data into our data set, it is not going to deviate so much from the first predictions. Okay, it is not going to show very much deviations in your outputs.
Okay, ma'am.
Okay, great. Okay, this is again a problem. This is a perceptron question. Okay, firstly, you are given a data set that is being predicted. This is the data values. 1 is predicted as +1, 1 -1 is predicted as -1, and -1 0 is predicted as -1. And your initial vector is 0 0. Okay, and you want to know which of the following statements are true. Okay, there are two questions from the options that we need to conclude in. One, when will it converge? Second one, which is the label that could be predicted for the data point 2 - 1. Okay, these are the two questions that we need to answer. So the first part we'll need to know which is the converging vector, right? Weight vector. Only then can we predict the value. So first, how do we know if the algorithm will converge or not? How do we test that? How do we test for the convergence of a point? Or sorry, convergence of an algorithm? How do we do that? When is there a need for updating your weight vector in perceptron?
By using W transpose XIY.
Okay, sorry, I was not able to catch you. Can you repeat?
Yeah, means when we encounter a mistake like predicted is 1 and actual is -1 like that, then we need to update our weight vector.
Yeah, when there is a misclassification, that is when you need to update. Okay, how do you measure the misclassification?
By calculating W transpose XIY.
By calculating W transpose X into
Y.
Y. Yeah, you calculate that, and if that value is less than or equal to 0, you say that the point is misclassified, right? If it is a positive value, you would say that it is not misclassified. And what is the update that you would do? How
Like
is the
previous weight vector plus
huh.
x into y.
Yeah, perfect. You update using the rule new weight vector is equal to old weight vector plus y into x. Okay. Now, can you calculate for each of these points?
Yes, ma'am.
Huh. Calculate y into w transpose x and see if they are less than or equal to 0 or not. That's the first part of our algorithm. You want to know if y into, that is for the first point it will be plus 1 into w transpose x. So 0, 0 into 1, 1, right? W transpose would mean you write it like 0, 0 into 1, 1. That one into y. That one into y would give you the correctness of classification. What is the answer that you're getting? Simple, right? 0, 0 into 1, 1. What will happen?
0.
0. 0 into 1 is
0.
going to be 0.
Yeah.
Okay. Since it is 0, is it correctly classified or misclassified?
Correctly classified.
No, no. If it is less than or equal to 0, it's misclassified. Okay. You include 0 with misclassification.
No,
It
ma'am.
should be a positive. Huh?
What you said? If my W transpose X is equal to 0, I will. It is classified into 1 or 0. Which class?
No, no, not like that. You oh, okay. It is classified into the positive class, plus 1.
That's only now. Yes.
Oh, okay. So actually, this is not correctly classified. It's misclassified because what you are getting for y into, okay, maybe I'll show the answer. That will be more easier for you. If we are actually calculating y into w transpose x less than or equal to 0. Okay, when we calculate y into w transpose x less than or equal to 0, you are getting that your point is misclassified. So when you look at the first point, your first point is classified as plus 1 into w transpose, that is 0, 0 into your x vector, whatever is your data vector, that is 1, 1. Okay, now if you do this calculation, what you are getting is that the answer is 0. Since the answer comes into the misclassification category, we will have to update the weight vector using the update rule. That is w is equal to, this is w old, okay, w old plus y into x. So w old is 0, 0, 0, 0 transpose plus y is 1 into x is 1, 1. Okay. So when you do this, your updated vector is going to be 1, 1. Now with this updated vector, you will calculate the precision of your classification for the second point. What is the second point? Second point was 1 minus 1. It is classified as minus 1. Okay. So 1 minus 1. This is again minus 1 into y into w transpose x. So y minus 1 into 1, 1 transpose into 1 minus 1. 1 minus 1 is your data point. Now this would result in again minus 1 into 1 minus 1. That is again 0. So this is again a misclassification, and you would again update your weight vector in the same manner that you did before. So W is equal to W old plus Y transpose X. So W old plus Y transpose X is going to be what? This one, the previous weight vector was 1 1. So 1 1 plus Y is minus 1 into your X vector was 1 minus 1. Okay. On updation, you are getting the new weight vector as 0 2. Again, with this new weight vector, you would look at the classification of your third last vector. What was your last vector? Last vector was minus 1 0, and it is predicted as, or it is classified as minus 1. Okay. So with this new vector, with this new weight vector 0 2, if you are calculating this one, so y was minus 1 into W transpose is 0 2 into, you get your weight X vector as minus 1 0. So into minus 1 0. The answer is that answer is again 0, right? Minus 1 into 0, no? Okay. Minus 1 into 0 it is. So it is again a misclassification, and you will end up updating your weight vector again. What is the updation? The updation states using the same rule, W old 0 2 plus Y minus 1 into X is minus 1 0. So you are getting your new weight vector as 1 2. Now you want to know if this is your last weight vector, you want to know if it will converge at 1 2. How can you confirm that? You need to check for the same thing. You need to check for the correctness of your classification using the same rule that you applied before. Now going through the same process, that is Y into W transpose X. If you are calculating that for each of the 3 points, you are getting every value as positive. Okay, greater than 0. That would mean that W is your correct weight vector, and the algorithm would converge it. Perceptron would converge at that weight vector 1 2. Is it okay?
Yes, ma'am.
Okay. And then to calculate, so your option here that is going to be right is the algorithm will converge at W is equal to 1 2 transpose. And to know what would be the label for the data point 2 minus 1, with this weight vector, that is with the weight vector 1 2, you calculate what is W transpose X. Okay, so the weight vector is 1 2 and your data point is 2 minus 1. So upon calculating, you are getting the value as 0. And when will you put the label as plus 1? When W transpose X is greater than or equal to 0, you predict it into the positive class, and when W transpose X is less than 0, you would predict it into the negative class for a perceptron algorithm. Okay?
Can I ask a question here?
Yeah, please.
Yeah, the first point is initial weight vector was 0 0, isn't it?
Yeah.
And then first point was just slightly go up. Uh,
Yeah, sure.
yeah, x1 was how much?
X1
x1
was
was
1 1.
1 1 1. So
Yeah.
1 comma, in that case, if you start with a weight vector initial of 0 0, the
Hmm.
first one will be always wrong, no? Miscalculation. If you are not considering 0 as a
No,
plus
but
1.
then, yeah, right. But then they have given that we need to start with 0 0. The
Okay,
initial
but
vector we can't change.
no, but I understand that. But
Okay.
in that case, 0 0 into 1 into 1 0, is it a misclassification or it's a right classification?
It's a
0 can be treated as
misclassification.
plus 1. No?
No. When you're calculating W transpose X only, okay? When you're doing that, if that is greater than or equal to 0, you classify your data point into the positive class, and if it is less than 0, you classify it into the negative class.
So this is
Okay.
equal to 0. No? This is equal to 0. So will that
No.
not be treated as plus 1?
That is just for direct classification. When you want to check for the correctness of the classification, what you do is you use this rule, Y into W transpose X less than or equal to 0 for misclassification. When you check for if your classification is already right or not, you are using this as your updation rule, or this
In
as
that
your
case,
accuracy rule.
0 0 0 0 initial vector will always give you a wrong this thing for the x1 first point
Yeah.
you take, always give the miscalculation.
Yeah, that's
Isn't
okay,
it?
right? Yeah.
Am I right? Am I
Yeah.
telling it
Yes,
right?
yes.
Any
Yes.
first point, any point you take, first one will be always misclassified,
Yeah,
isn't
you
it?
will have to update it at least once.
The first point by default will be misclassified.
Yeah, according to this, yes. But then what will happen is, if you are actually right, what the perceptron algorithm would eventually get into that particular weight vector, so that you reach into this proper thing only again. You, like, it will make a roundabout and come back here only. It will like swing and come back here. I mean, it will go back to that old weight vector.
So that's why actually I got some doubt here. By
Hmm.
by default, the first point will be always wrong.
Yeah,
You take a
by
0, 0
default, it's
vector,
going to be 0, 0. Yeah, it's
always
going to
0,
be
0,
always
and
wrong.
always wrong.
Yeah.
So that this is the approach you should have. I was calculating actually 0, 0 as +1. I was proceeding
Oh,
that
okay.
way,
Oh,
but I
then
was
you
also
wouldn't
getting
have
the
to
answer.
update at all.
Yeah, that was also converging in any case
Yeah,
to
it
all the
will
problems.
converge. Perceptron will always converge, right? That is a rule.
Mm.
Perceptron will always converge. It is not like
But
it will
answers
never
will be
converge.
but the answers will be same and answer will be different.
No, no, it will always converge at that same point. It will only converge at 1, 2. If you are saying that it would converge at 0, 0, then that would mean that there is no option at all like that. See, there is
Correct.
no 0, 0 at all.
No,
So
I'm
it
saying
is,
that even the answer, if I take that as a +1 also, still
huh?
it will converge at 1 and on comma 2.
No, when if it will actually converge at 0, if the first point converges, what will happen is your weight vector would remain 0, 0, right? So every of your point will have the same weight vector, and eventually every point will be classified correctly only.
No, I'm saying the first one is right. If I take for
Huh,
the argument, say, let us take 0 as +1, okay? Then
huh,
we'll move to the second one. We'll
huh.
move,
But then you are not updating your weight vector, right? If this is a right
no, I'm not
classification,
updating the first weight vector. Let it be 0,
huh,
0. Then
huh,
we'll go to the next one.
huh. Then that
Okay,
will
in that,
again be 0, 0, because
yeah,
you are multiplying, right?
yeah, but ultimately, okay, you are right. I think it will never get updated.
Yeah, it will always be 0, 0. It will keep on going into 0 because we are multiplying here. Like, if
Okay.
it was one addition at least, then there's a possibility. But since this is multiplication, we will never update the 0, 0, and it will keep on going into that loop of 0 only. Like, every time it will say it will converge at 0, 0 only.
Actually, I was doing it the other way around, say 0, 0. In this
Huh?
point, x3, you will see it is -1. The level is -1 for the x3, isn't it? Go up
Yeah,
slightly, the x3 is number.
this one.
So, no,
Okay.
the initial x1, x2, x3, the
Yes,
values.
yes. Okay.
Yeah, you
Yeah.
would see the number 3, number
Huh.
2. Number 2 itself, there is a change. So, I'll change, update x2.
But you can't update when it is saying that it is going to converge at 0, 0, right? We don't unnecessarily update. We only
I'm
update
saying,
it.
yeah,
Huh.
I'm assuming that 0, 0 is +1.
Okay.
So I'll go to x2. X2 it is -1. So I'll update x2. I'll
Okay.
update x2 with 0, 0 plus -1 plus 1. So the new weight becomes -1 plus 1. So then with
Oh,
-1 and +1, I'll do this. Then it will change the third one. So I was
okay.
working in this way. Answer seems to be I think the same.
Oh,
Yeah,
okay.
ma'am. This was the same doubt for me also. That's why I asked for you.
Okay. Fine. Maybe then there is another approach. I'll have to check that. I'm not sure.
We are just seeing this first time.
Okay.
This
No.
approach.
Okay, then maybe I'll ask. Okay, I'll verify that. Okay, if
Uh,
actually Samruddha is actually
Because
doing something,
I
I'll
was
verify.
doing in this same manner, and
Hmm.
all answers were matching actually in this way.
Oh, okay. Perfect. I'll check then. Yeah, maybe.
Mm.
Yeah, there can be alternative ways, right? Yeah, sure. I'll give a check.
Okay.
Okay. Next question. A kernel regression model with a polynomial kernel of degree 2 is trained on the following data set, okay, with three features. Let the optimal weight vector be W star is equal to phi of x into 1, 1.2, 0, 0.7, negative 0.5 transpose, where phi is a transformation mapping corresponding to the kernel. Kxx dash is equal to x dash, x transpose x dash plus 1 the whole square. Compute the predicted value y pred for the new data point triple one and okay, enter the answer in one decimal point. That's fine. Okay, how do you do this? What is the approach? What should we calculate first to find what is the classification? What do we need to calculate first?
we can just directly apply the formula.
Yeah, the
Huh.
111 with 123 and then 11 with 456
Yeah.
and multiply that with 1.1, 1.2,
Yeah,
0,
Yes.
that
0.7.
that vector is
You'll
alpha,
get the answer.
which is given
Yes, yes.
here. Yes.
Perfect. Yeah, this is your
Express,
alpha values. Yeah,
yes.
very good. These are your alpha values with corresponding to each of these vectors. That is corresponding to 1, 2, 3. You would substitute that for x transpose into x dash. That is 1, 1, 1 plus 1 the whole square. You will calculate this value corresponding to each of these vectors. Right? You will calculate for 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 1, 3 and 6, 5, 4. You will get 5 values and each of those 5 values are multiplied with your alpha values that are given as the weight vectors in W star. Upon adding that, you will get the answer. So
Yes.
when you substitute first 1, 2, 3 and then give 1, 1, 1, you will get the answer as 49. This is just multiplication. 1 into 1 plus 2 into 1 plus 3 into 1. So you will have 6 plus 1, 7. 7 the whole square is 49. Similarly, for the next vector 4, 5, 6, you will get the value as 256. So you can calculate this particular kernel, right? Kernel value k x x dash, that is x transpose x dash plus 1, where x dash is your new data point and x transpose are each of these vector values in this matrix. Read as column. You will get each of the kernel values and each of these kernel values are actually multiplied with the weight vectors given here. That is 49 into 1 plus 256 into 1.2 plus 625 into 0 plus 49 into 0.7 plus 256 into negative 0.5. Whatever is your answer, that is going to be your prediction. Okay, that's going to be your y prediction. Okay, okay, right? Fine. I hope
Yes,
this.
ma'am.
Okay, great. A coin is flipped 1000 times and it lands on heads 150 times. You use a beta 1040 prior to estimate the true probability of heads. Given these observations, calculate the posterior mean of the probability of heads. How do we do this? Something that you have already done in stats too, probably. What estimation are we doing here? No idea?
Posterior distribution.
Yeah, yes. We have to find the posterior distribution. By just looking, can you tell me what is a posterior distribution?
The beta is given as a prior, and
Huh.
likelihood is
Is 150 by 1000.
Likelihood is,
Bernoulli distribution.
yeah, with what would you say? What would be that value be? You can say binomial. It's repeated 1000 times, no? So it's
Yes,
fine to say binomial.
with a 150 head.
Yeah, so
At
p raised to 150 into 1 minus p raised to
850.
850. Perfect. Into, that is your likelihood, into your prior would be p raised to
10 minus 1.
10 minus 1 into 1 minus p raised to
40 minus 1.
40 minus 1. Now, if you just combine the similar terms, you will have p raised to 160 minus 1 and 1 minus p raised to 890 minus 1. Right? That is a beta distribution with parameters 160 and 890. Okay?
Yes, ma'am.
Now, the it is given actually as a hint in the question itself. The mean of the beta distribution is alpha by alpha plus beta. Alpha is 160 here, beta is 890 here. So your posterior mean will be 160 by 160 plus 90, which is 0.152, 0.152. Okay?
Here, actually, you can straight away add these ones and zeros, and
Yeah.
you can do that.
Yes, yes. You can do that. Okay. This is your next question. Consider a single layer neural network comprising of two neurons in the hidden layer. The parameters are given below. Okay, W1 of 1 is 1 by 2, W2 of 1 is 1 by 2, and W1 of 2 is 1, and W2 of 1 is minus 1. And the out vector weight is 2 minus 2. This represents the weight associated with the jth neuron point for the ith point. Suppose we are solving the regression problem Then determine the output of the neural network using ReLU as your activation function for the input 1, 3. So what is our ReLU function? What does it say? I mean, that is the only catch here, I guess. What is a ReLU function? Someone? Anyone?
Is what regularized linear unit or something like that?
Yeah. Oh, I wasn't asking the expansion. Yes, it is some rectified linear unit. Not that. I was
Rectified, yeah.
asking what is the function of it, or how does it classify?
So it will take all negatives to 0 and positives as it is, isn't it?
So it will actually give you the output as a maximum of 0 or whatever is your positive
Yeah,
value.
whatever is.
Yeah, but that is how ReLU works. So in this question, first what do we have to do? We need to pass this data point through the first layer in the starting, then pass it, find the ReLU or what is the Z value. Similarly, pass it through the second weight vector, find the Z value, and whatever you are getting, that is going to be your output value coming in that. To that output Z vector, you would multiply it with the weight vector to obtain the output. I mean, to obtain the final answer. Can you try? Maybe. Just multiply
Yes.
1, 3 with 0.5 as your first step. What is the answer that you're getting?
So 1 and minus 1, isn't it?
Yeah, you will have
1 and minus 1.
right? 1, 3 is your input vector, right?
Mhm.
1, 3 is your input vector. You are multiplying with 1 by 2, 1 by 2. That's the first layer, no?
Yeah, right.
So what will we have?
It will get 2, isn't it?
Yeah, UB will get 2. Perfect. So maximum of 0, 2 is
2.
2 only. So that's your first data. That's your first point. Okay. Now the second is when you pass that through your second layer. If you're so multiply 1, 3 with 1 minus 1.
So it will become minus 2, that will be 0.
Yeah, that will be 0. Okay.
1 minus 3 is minus 2, 0. 2, 0.
Very good. So you got your output vector. So you got it as 2, 0, right?
2, 0.
Now
Yeah.
multiply that with the weight vector, the given weight vector. Sorry. Yeah.
So it will be 4.
It will
2,
be
0 into
4,
2
4.
minus 2, yeah, it will be 4. 2 into
Yeah,
2, 4.
it will be 4. Yeah, perfect. That's your answer. I mean, neural network is simple, I guess.
Just can you go slightly down? Yeah, I'll just set the.
Huh.
Okay, fine. Thank you.
Yeah, great. Okay, so this is a little elaborate problem maybe. There is a data set given and you are using the naive-Bayes algorithm to actually predict what would be the answer or what would be the prediction probability if the outlook, you are given what are the independent variable values. Okay, outlook is going to be overcast, temperature is going to be cool, humidity is high, wind is weak. Okay, that is your value, that is your evidences that you have with you, or these are the values that you have with you. With this you want to predict what will happen for if we whether we will play tennis or not. Okay, you want to give an yes or no answer, you want to classify that. For that you are using a naive-Bayes algorithm. So what do we do? As in the class, starting of the class, we said, what is the basic assumption of naive-Bayes algorithm? We are considering that each of the independent parameters are we are considering the parameters, I mean, the variables are as, why is it called naive-Bayes? It was just told.
Independent.
Yeah, they are not related. Yeah, that's how we are considering it. Okay, how do we go about this problem? Or what do we have to do?
We can apply this conditional probability and
Yes, we have
like
to apply the.
we'll consider all the no's and all the yes separately, and then do the that the whatever overcast, cool, high and weak find out the probability given that it is yes, then
Yes.
given that it is no, and then add that, put that in a denominator, and
Huh.
numerator you take only the yes.
Yeah, perfect. That's your Bayes rule, right? You are applying the Bayes rule. You are
Yeah,
using the
base rule, right?
conditional rule and
That's
applying
true.
the Bayes rule. Yeah. So what I'll just go, since you know the logic, I'll just go through the steps. Okay. The first thing is you need to calculate what is the probability of yes, and you need to know what is the probability of no. So in the given data, we have six yeses. 1, 2, 3, 4, 5, 6. Yeah, we have six yes and four no's. So your total probability, just without a condition, just the probability of yes is going to be 6 by 10, and probability of no is going to be 4 by 10. Okay. Now responding to this yes and this no, to each of the parameter values that we have here, okay, each of the variable values that we have here, we will calculate probability of outlook given yes and outlook given no. We will calculate probability of, sorry, overcast given yes and overcast given no, and we will calculate cool given yes and cool given no, high given yes, high given no, and probability of weak given yes and strong given yes, sorry, no given yes, weak given no. Okay. We will calculate each of these probabilities corresponding to the data given in the table above. Okay. Each of these probabilities are then finally multiplied together to obtain what would be the conditional probability that he just stated. That is probability of these happening when they will play a cricket. Sorry, when they will play tennis. Okay, when they will play tennis, what is the chance that these would be the combination that would be happening for our different variables? We will calculate that as well. We will calculate what is the chance that they'll, if they are not playing tennis, what is the chance that we will get such a combination for outlook, temperature, humidity, and wind. After obtaining these two values, we will apply directly the Bayes rule, which is probability of the parameter or the variables given like this, given yes divided by probability of these particular combinations happening given yes plus these particular combinations happening given no. Do you want to do once, or is it okay? Like, do you want to calculate it by yourself once?
Okay, ma'am, it's okay.
It's okay. But actually, before going for the exam, you should sit and do, okay? Don't skip like this.
Okay, ma'am.
Next is consider a logistic regression model that has been trained for binary classification. Given a data point, it would return 1 as a predicted label if the output probability is greater than 0.55. Otherwise, it will return 0. Okay. What will be the predicted label for the test data point 1, 2, assuming the weight vector is 7, 4. Okay. So you will predict the predict the data point into the positive class if your probability is greater than 0.55. Otherwise, you will put it as 0. Okay, you will put it into the negative class. How do we calculate this? Okay, what is the logistic function? What is the sigmoid function? If you're not familiar with the logistic function term.
1 upon 1 plus e
Huh.
to the power minus z.
Yeah, what is it? Right, yeah,
W
right.
transpose
The
X.
transpose x.
Perfect. So you are given W already, right? You are given 7, 4 as your W value. You are given X
That comes to
also.
15. That comes to 15.
Yeah, that comes to 15. Okay, very good. Then what you have to calculate is simply 1 by 1 plus e raised
1
to
plus 1 e to the power minus 15.
1 plus 1 e to the power minus 15. And
Minus
if that value is greater than 0.55,
Then it is plus 1, otherwise it is 0.
otherwise it is minus 1. Easy, no? So you're actually getting it as approximately close to 1. It's 0.99 something. Since it is very much greater than 0.55, we will classify this as a 1. Okay, we will classify the data point 1, 2 into the positive class. Okay, I guess this is the last question or something. Okay, consider a single iteration of ADA boost that is run on the 5 sample coins with labels 1 or minus 1, starting with uniform vectors. Okay, there are two classifications happening, that is through H1 and H2. You are given the true label also. Which classifier has a lower training error? Okay, how do you calculate the lower training error?
Just compare the predicted against the true level for H1 and also for H2, and then find out the error.
Okay,
In
can you
in
tell me
first
how
case,
many?
yeah, in first case, basically 1, and then two mistakes are happening, isn't it?
Two mistakes are happening out
Yeah,
of five.
two out of five. It's a point
Two
four.
out of five. Yeah. Okay.
Point
And this
four.
here,
So here it is, one,
four.
two, three,
Ah,
four.
four. Four out of five
Yeah.
are
So
wrong.
point four
So
and point eight.
point four and point eight. So it
So
should be.
error will be no ln of
Okay.
one minus e by one by e.
No, that's okay. Which has it? Which will have that lower training error?
Yeah,
We
that
can
we can do.
otherwise
Yeah,
also say,
H1,
right?
H1 is lower.
Yeah, H1 is lower. Now, next, what you want to know is the classifier. You chose H1, okay? The classifier with the lower error rate is used in the next round. Determine the classifier H star obtained at the end of this round. How do we do this? Using the formula that you just stated now.
So it will
Okay.
be sigma alpha one H1. Sine
Huh.
of sigma alpha one H1.
No, you were saying the log formula, right? I mean that.
Yeah,
That
yeah,
was the
and the
right one.
second part I'm saying. I mean the
Huh.
so if you calculate that, you can arrive at this.
Okay, the error value that we are considering is zero point 0.4, right? H1 will have the lower training error. That
Yeah,
is what is considered into our next model. That is what is trained for us. So we will consider H1. So our training error is going to be 0.4. So log of 1 minus 0.4 by 0.4 is
yes,
what?
yes. It will
Yeah,
be
that,
it will be 0.6 by point
yeah,
4, 1.5,
0.6
ln
by
of
4.
1.5. Yes,
ln of
that will become
1.5.
0.202.
Yeah, ln of 1.5 into, there is one more value, right?
Which one is that?
Into zero point 0.5. You need to multiply that with 0.5 to get your alpha value, right?
Uh, just a minute. How are you getting this 0.5? Acha, okay,
How,
the initial was 0.5, fine, fine.
Huh.
Into
So,
0.5, right?
yeah, so you will have your predicted value or your, what do you say, your classifier H star as sine of alpha into alpha you just obtained now, that is 0.5 into log of 1 minus 0.4 by 0.4. You will obtain this as 0.20.
Correct.
Huh. So your H star, the answer to this question is sine of 0.202 into H1, since H1 is the classifier that we are using. Okay, any doubt? This is the last question actually. So any doubt?
ma'am, can you go back to neural networks question?
Yeah, sure. Neural network. This one, right? Yeah.
I don't understand this question. Can you explain once?
Yeah, sure. This is your weight vector, okay? This is your first neural network.
Yes.
On the top, with whether it is when it is written 1, that is your first neural network. You are inputting this data point 1, 3 into that network, into that layer. Okay. So
Yeah.
what will be the output of output through that layer? Output through that layer is going to be 1, 3 into 1 by 2 into 1 by 2. Okay. You will multiply these two. So you will have zero point 0.5 plus 3 into 0.5. 1 into 0.5 plus 3 into 0.5.
Okay.
Okay. And that will be what? 4 by 2, no? Like 1 into 1 by 2 plus 3 into 1 by 2.
Okay.
Okay. And that is going to be 3 plus 1 by 2, which is 4 by 2, and you will get the answer as 2.
Hmm.
Now, if you are passing the same data point through the second layer,
Okay. Huh.
when you pass it through the second layer, what will happen? You multiply 1, 3 with the weight vector 1 minus 1.
Okay.
So, what we will have is 1 into 1 plus minus 1 into 3.
Okay. Huh, yes.
So 1 minus 3 is going to be
That's the minus two.
minus 2. Now they have told that we are actually passing these output through what? Through we are determining what will be the output through the ReLU function. Okay, and
Yeah.
the ReLU function actually tells you to take either 0, I mean maximum of either 0 or the value that you are getting.
Hmm.
In the end, you need to get the positive value. You don't want a negative value as the output.
Correct.
Okay.
Hmm.
So through first layer, when you are passing it, your answer is 2, right?
Yes.
So the maximum of that is going to be 2 only.
Hmm.
But when you pass it through the second layer, your output is minus 2. So
Yes.
maximum of 0 and minus 2 is going to be 0.
Zero. Yeah.
Okay.
Hmm.
So the activation vector that you are getting is 2 comma 0.
Yeah.
And this activation vector you would multiply with the output value. So what you will have is 2, 0 into 2 minus 2.
Okay. 4
Okay,
means
so that is 4 plus 0, that's 4.
Thank you, ma'am.
Yeah, right.
Ma'am,
Huh?
ma'am, in place of RE, if we have something different terms, then how we can do like
Same
LU?
procedure. Just replace instead of that ReLU function, replace whatever function is given.
Ma'am, the
So in
like
total, we have three methods, right, ma'am? ReLU, TANH, and sigmoid.
Yeah, and usually either they'll give sigmoid or ReLU. I don't think they'll give TANH because
So tan H is not there in our
Okay.
syllabus.
yeah, I don't think that'll be given.
Tan H is not in the syllabus.
But if it's given, just use a calculator. It is there in the scientific calculator, no?
yes, ma'am.
Yeah, so
Ma'am, for sigmoid
Okay.
also we can do same process.
yeah, you will just substitute 1 by 1 plus e raised to minus z. That's your sigmoid function, right? So yeah, after getting this answer, you will substitute that value. This is again W transpose X only. So you will substitute this, whatever answer that you are getting, into the sigmoid function.
Okay, ma'am.
The same
Yeah,
question if
just
it is sigmoid, how do you do?
input, your output answer is 2 only. You still have W transpose X. Your sigmoid function is what? 1 by 1 plus e raised to minus W transpose X, right? You got what is W transpose X as?
So instead of one divided by 1 plus e to the power
Yeah,
minus 2, isn't it? And the same second one also
same.
same 1 divided by 1 plus e to the power plus
Yeah,
2.
plus 2.
Since it is
Yeah,
minus 2.
that's it.
Then accordingly you can arrive at square.
Yeah, that will be
And
your
then
weight
multiply
vector.
that with 2 minus 2.
Yeah, you will get your
Get
weight
W two.
vector h1 and h2. You multiply this whatever activation function that you are getting, you multiply with that your input.
Yes.
Sorry, output weight vector. You multiply that with your output weight vector.
Okay.
So you will get the answer. That's it. Is it okay? Every questions?
This particular PDF is you can send it on the chat box.
Okay, I'll share it, but then I'm not
Yeah,
sure
you
if
can share it in this chat box. Then we can
yeah,
use that.
I'll paste this. This is
Yeah,
actually an app.
just paste that.
I'll
Yeah,
paste
just
this
paste.
link. But yeah, maybe we'll when we circulate this in the Nilgiri space, we'll add the whole PDF. Okay, as such.
Okay. But how to get into the Nilgiri's page and all that?
Just go to the YouTube and see. Right, type
Also,
IIT
I'll be
Nilgiri.
sharing the GSpace link in the chat box. Okay.
Okay.
Because we do not know how to reach Nilgiri's.
Yeah, that's fine. Okay. Can I actually stop the presentation? Is there any doubt here?
Can we once again roll through the entire question set? Actually, I joined late.
Yeah, sure. Okay.
Just a minute.
The first was what
First
was a
one,
regularization term,
declaration. Okay.
or what does it imply? The second was what is a pure node. Okay, and when you study, try to learn related terms also, like what is entropy, when is entropy zero, when is it one, or what is impurity, what is the cross entropy formula, like that. Okay. Um, Next is there were three weight vectors given. We were tried to actually classify which regularization is used in each of the terms. Okay,
Okay, fine.
since there was a zero, this was lasso. Since W1 was having a lesser weights than your second one, this was considered to be ridge, and this was your linear classification, like one without any particular regularization. This was when we applied the Lloyd's algorithm. This was the first centroid, the first round of centroid. We are trying to classify the data point 33 after the second iteration. That is, we'll calculate the centroid again, taking the averages. We'll calculate the centroid again. After that, we'll try to calculate the Euclidean distance, and whichever has the smallest distance with the data point 33, we'll classify that there. That's what Lloyd's algorithm says. This was a kernel relationship given. We wanted to project it into a lower dimensional space. So we asked which is the bare minimum polynomial that you will have to apply. Since the highest degree of this model that is used here is degree 3, we will have to use a kernel PCA with a degree 3. And since it is a non-linear relationship, we cannot use a standard PCA.
Correct.
And then we went about, okay, what does how does using ensemble methods help with weak learners? They actually help you to improve the accuracy, because using an ensemble method will help the weak learners to learn from their previous mistakes. Okay, and these are the two models given for a cubic polynomial process. So we wanted to know the behavior of these two models. Okay, since model 1 is a linear model, it is not able to capture everything that a cubic polynomial is handling. So it is probably give you a higher bias, and it will give you lower variance, and eventually it will underfit your data. And model 2, since it is given to be a 5-degree polynomial, and since it is actually unnecessarily including more data, increasing the complexity, and including your noise data into understandings, it will overfit our whole model. I mean, it is a overfit our data, and it is likely to produce a higher variance with a lower bias. That is general for any overfitted model, I guess. Now, from here you are there, right?
Yeah. From here I was there. Fine.
Yeah. So this is okay. This is again
No,
a
this is
puzzle
okay. This is
problem.
okay. This is okay. Do we discuss this one? Maybe there is a doubt here. You can clarify later on.
Yeah. Is Amrita actually going to discuss anything more? Is there any need that you guys want? Is there any topic? Okay, then I'll put it in the G space. Okay, I'll clarify this answer in the G space. Does that work? There is a G space given
Yeah.
here.
Also, I
Can.
have
Yes,
pasted the link of the G space of chi-square, which was the statistics club under Nilgiri House earlier, which is now Nilgiri Statistics Community. You guys can join, and we'll be updating the YouTube video and the PDFs, everything over there. Okay.
Just
Just one question here. In case of bagging,
hmm.
that 1 minus the probability of 1 minus 1 by n to the power n, that's number of the percentage is how much 1 minus 1 by e is the probability of a particular things getting repeated for to removing the correlation. So that figure is 36% or 34% in bagging. What is the probability of same thing is getting figure getting repeated? Is 66% or 64%? I had a doubt actually. In bagging, there is a probability of same number getting repeated, huh?
Okay.
Which is root over d. So if the sample is 100, you usually take this thing of root d, which is say 10. If n is 100, you would take 10 samples in one bag. What is the probability of that thing getting repeated? Is how many number of
Are you
things?
talking about that one minus one by e?
Yes. So what is that figure coming out to be? Is 36%?
It's around 0.342, so you can approximate
34%. 34.
so six.
So it's 34 and 66.
No, that 1 minus 1 by
67, I
1
guess.
minus.
So that obviously
Mhm.
100 minus other one. If you take 34, if it is then it is 66. If it is you are taking 35, then it is
So
67.
1 minus
Sorry.
e is approximately around 36.8%. So you can approximate it as 37%, and the other one is 32 or 33. 33.
So what is that figure in that case? What is the probability of same? How many numbers getting picked? Is somewhere it is written 1/3, somewhere it is written 64, 34%. So I think
So
that's
it is basically 36.8%.
36.8%. But approximately that is as good as 1/3.
Yeah, approximately
But to be precise, it is 36%.
36.8.
And 64% other way around,
Hmm.
which is not getting picked. Getting repeated is 64%. Right.
Okay, I've pasted the PDF. Okay, not the PDF. Yeah, the link of that.
Okay.
You can
Thank
maybe
you.
try accessing it. Yeah, welcome.
Thank you.
Okay. Any questions, guys?
ma'am,
Will
could
you be
you
taking
please?
some more sessions like this?
Do you
Uh,
need more sessions?
I don't. I just asking.
No, I was also asking. Like we We are not.
We discussed one. This is a PYQ. You have just discussed, no?
Yeah, this is a PYQ of 2025. And
Okay.
actually, Sami Brother, as a starting, discussed the topics also. A few revision topics. He went through the topics.
So I started with a few binary classification techniques, and then we switched to PYQs.
There are some PYQs. If you have any doubt, we can put it there.
Yeah, sure. We'll
Yeah,
write
sure.
that.
Ask it over there. We'll be always there for answering, and other members as well. There are few of them are also have completed this and in degree level, so they can also answer.
Because some of the answers are a bit ambiguous. The answers are not right. It's if you go to discourse, you might find them corrected. But if somebody tries the PYQ through those typical portals, what do you call that, which is available to
Yes,
us for
correctly.
solving problems. So their answers are, the answers are wrong in so many questions. So we need to actually get the right
Very.
answer.
Yeah, yeah,
So
sure. You
maybe
guys will.
maybe we can approach the discourse. We will get the answer, but we do not have so much time in searching the discourse and see whether it's right or wrong. So those are some of the queries I think we can.
Sure.
Yeah,
Put
sure.
it over there.
We'll
Uh,
answer as much as we can. Sure.
Thanks. That will be great.
Yeah.
Anything else? I guess someone is trying to tell something. Guys, any questions apart from this?
Ma'am, could you please discuss one question here related to hard margin?
Sorry, I can't hear you. Can you repeat again?
Yes, ma'am. Ma'am, could you please discuss question related to hard margin FEM?
Actually, there is one explanation given in that question. Before pasting it, I have actually put it up. Can you actually take a look at that? There is a problem discussed and given already with an explanation.
Okay, ma'am.
And ma'am, the weightage will be more for the 9 to 12 weeks, right? For the final end term.
Yeah.
Yeah, 50% for 9 to 12th, and apart from that, rest of the part will take 50%.
Okay. Thank you.
Okay. Yeah. Thank you. Can we wrap up?
Okay, guys,
Yes.
thank you for coming and discussing.
Okay. Thank you very much.
Yeah. Thank you for joining.
Okay, thank you, sir.